In this lecture, we're going to look at some more examples of parametric equations with the goal of seeing what their graphs look like. We're going to focus not just on plotting points, but also thinking through what the equations are telling us. And along the way, we're also going to see some of the more interesting properties of this kind of equation. Now, this set of equations is a little unusual. At first glance, you might expect it to have some kind of quadratic behavior based on the two quadratic expressions. But before jumping to conclusions this early on, let's take a look at some points. When x is 0, when t is 0, x of t is 0, and y of t is 0. When t is 1, x of t is 1, and y of t is also 1. 2 gives us 4, and 4, and 3 gives us 9, and 9. Now if we graph these, you'll see that rather than a quadratic graph, we get a linear one. So now let's go back and think through the two equations again. All right, since both formulas are the same, we should expect the two components to be increasing at the same rate, which does describe a linear relationship. And we'll circle back to this set of equations in a later lecture when we talk about the derivative of parametric equations, and we'll see that the derivative is constant, which again is a sign of a linear relationship. So before we move on to the next set of equations, take a minute to think about what's going to happen when the t values are negative. Since both the x and y components are being squared, we still get the same values, but we're going to get them in the reverse order. Negative 1 is going to give us 1 and 1, negative 2, and negative 3. So if we think about a particle moving along the graph, it starts outside, comes in to the origin, and then turns around and goes back out along the same linear path. This set of equations should look a little familiar. In our first series of lectures, we looked at the graph of x equals cosine theta, y equals sine theta, and saw that that graph was a circle. It's reasonable to expect this graph to follow a similar cyclic path, but we need to investigate what effect the 2 and the 3 are going to have. So again, based on what we already know, I'm going to focus on the four values of theta that give us the extreme sine and cosine values. That's 0, pi over 2, pi, 3 pi over 2, and finally 2 pi. And you can kind of see what's happening here. When we did this with the sine and cosine, our maximum and minimum values were 1 and negative 1. Here we're seeing 2 and negative 2, which corresponds to the 2 parameter, and 3 and negative 3, which corresponds to the 3 parameter. So to make the graph a little clearer, I'm going to use a scale of 1/2 for each grid line. So that puts our 5 points here, 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 and here. Now we can see when we connect the dots here that our graph is going to be an ellipse. And we'll be showing that this equation is actually equivalent to the rectangular coordinate equations as a question in the exercise set in the online classroom. Now, the first set of equations here is one that we've seen many times now. It's just a circle where theta goes from 0 to 2 pi. Now, the second set, on the other hand, looks significantly different. I literally reversed the formulas for the two coordinates. However, if we plot some points, again going from 0 to 2 pi, the graph starts at 0 to 1 using a scale of 5 units here, then goes to 1 comma 0 when theta equals pi over 2, then around to 0, negative 1, negative 1, 0, and finally back to the starting point when theta equals 2 pi. And again, you see, we get the same circle here. So what I want you to do is focus on the end result. Ultimately, while one graph filled in clockwise from starting at 1 comma 0, and the other filled in counterclockwise, the first one is counterclockwise, this one is clockwise from 0 comma 1, the final results are the same. Right, so the lesson here is that if we ignore things like speed and direction and look just at the final result, the parametric representation of a specific graph isn't necessarily going to be unique. In other words, we can have one graph and represent it multiple ways using different sets of parametric equations. So now that we've seen what parametric equations are and some of the things that make them uniquely useful, we're ready to start actually doing things with them. So in the next lecture, we're going to see how to convert between parametric and rectangular equations. Then we'll think about how to find the intersection of two parametric equations. And at that point, we'll be ready to start adding calculus techniques to the mix.